I'm Vinicius Ponte Machado from Federal University of Piauí, from Brazil, and I will present the work using clinical data and deep feature in renal pathologies classification. Now, we'll present our problem definition. So, in the United States of America, chronic renal failure affects between 11 and 20 million individuals, while in Brazil, there may be about 1 to 4 million people with this disease. The kidney pathologies treatment is expensive and can affect the working capacity even in young people, which end up causing an economic impact of the social security system. So our motivations are: assist the pathologist in defining an assertive diagnosis based on clinical data and the patient's renal biopsy image using machine learning. Using as input the join of clinical data and kidney biopsy image descriptor for each previously known diagnosis. Our objectives are: verify if the clinical attributes alone are capable of returning good results. Use several descriptive classifier images of renal pathologies together with clinical data. Check if the combination of one of more descriptor with clinical data is feasible. Verify each test learning algorithms best applied to the task of classifying renal pathologies. Algorithms combined with CNNs. Decision tree using entropy, random forest, SVM, MLP, random forest. 100 trees using gene coefficient, SVM, linear kernel with a maximum of 1000 interactions, MLP, 100 hidden layers with 100 neurons each, ReLU activation function. For data preparation, we use feature selector, enhancing the recognition rate with the least number of elements and that generates a set of similar features for objects with similar aspect, principal component analysis used, resampling, way to get around the problem of an unbalanced dataset, generating new samples in order to make it balanced. Now, we'll talk about the clinical dataset. One of our main concerns is quantity, both with regards to few examples of some classes and small amounts of samples. Here, in the right picture, we can see how many features are needed to describe the complete of 100 samples from the clinical dataset. We can view that only about 20 features are required to describe the clinical dataset. The image dataset has 71 images whose height and weight dimensions are varied. Therefore, not all clinical data have a corresponding image. In the left picture, we present the renal biopsy image samples from the image dataset, demonstrating the degree of variety of the available images. There are 28 diagnoses associated with the clinical dataset. To solve the dataset imbalance problem, we apply resampling. After the procedure, all classes contain 7 examples each. In our test, we use 2 types of database: pure set, contain only clinical data attributes, or only image descriptor, and a hybrid set has both clinical attributes and image attributes. Tests of the second type varied the number of descriptors. Proposed methodology. As we can see, the pre-processing step was unnecessary, as the result feature selector of the CNNs has a standard size, not depending on the image dimensions. In the CNNs, convolutional layers are composed of the amount of C of features with size D times D that extract the features maps when convoluted with input image or outputs from other layers. The output of the convolution steps is the feature map. These maps usually represent general features extracted from the image, such as color, edge, texture, and shape. Next, we concatenate the CG to the deep features and choose features through the mutual information selector. After this step, we perform the resampling procedure to balance the amount of examples per class by duplicate example of minority classes. Finally, in the next step, the process was classification. Test learning methods were decision tree, support vector machine, random forest, and multi-layer perceptor. To analyze the classification results, we build the confusion matrix. Then, from the elements of this matrix, we calculate accuracy, precision, recall, and F-score. We also calculate the kappa index, which is recommended as an appropriate accuracy measure to represent the confusion matrix properly. Each descriptor studied was combined one by one with clinical data to obtain those that return best kappa coefficient. The test cases were defined as follows: 1. Clinical data only. 2. Only one image description, no clinical data. 3. Clinical data plus image descriptor, range 1 to 4 description. Now, you talk about results and make some discussions. Figure in the left presents a comparison of the classified best performance in the three scenarios. 1. Using only CG features. 2. Using only deep features. And 3. The concatenation CG and deep features. The individual descriptors archive a kappa index that was rated as excellent. However, the results was significantly improved by concatenating them, reaching an accuracy of 95% and kappa of 98%. In the right, we can see the configuration that obtained the best results for each classifier. We observe that the best configuration includes CG plus deep features in all classifiers. We also observe that both SVM and MLP had their best results with CG plus Inception V3 descriptor. The figure shows some items of the random forest classifier confusion matrix using clinical data plus HOG descriptor. We observe in these figures that 2 errors made by the classifier were for disease that had 25 or more clinical data characteristics in common. These images are quite similar, which may have introduced the classifier to make these mistakes. However, it believed that inclusion of new image will make the classifier further improve in its height. So, we show our conclusion and some future works. Clinical data alone not archive the best results. Concatenation between clinical data and image descriptor is feasible and produces better results. Not all the learning algorithm tests are suitable for classifying renal pathologies within a hybrid data set. Resample was fundamental for the good performance obtained by the classifiers, but overfitting occurred. Thank you for your attention. Here is my contacts. Bye bye.